Last time we talked about what it means to be a conservative function. We came up with a variety of properties that are obeyed when you are a conservative force, rather. It all starts with a test. If you have a force that the curl of that force is 0 in your given coordinate system, then there is a scalar function u, which we will call the potential energy, that can be defined as negative the work integral and going from some arbitrary reference point that you decide on, where you are choosing that point to be where the potential energy is equal to 0, out to your location, and that then tells you the value of the potential energy at that location. This then is equivalent to saying that the potential energy function is something where if you take negative the gradient of that function, you get back the force. So, and if you have conservative functions, so if only conservative functions, or only conservative forces, I should be saying, act on the object, then your change by the work energy theorem, the change in your kinetic energy then is equal to the net work being done on you, the sum of all the individual works being done if there are multiple forces acting on you. But if each of those forces are a conservative force, each of them will have its own potential energy function that you can write down, such that each of these is negative the sum of the individual changes in the potential energy. Again, changes in potential energy relate to work, which is why you're allowed this free reference point. Or that the ultimate change in kinetic plus all the potential functions equals 0, which is the conservation of energy. If you have, say, non-conservative forces as well, well, then you have that the change in kinetic energy is still equal to the net work that's done. That is still true. That is the work energy theorem. It doesn't matter what kind of force is acting on you. That is still always going to be true. But then I can break the sum up into the sum of conservative forces, and then there might be work being done by non-conservative forces. The conservative forces all have their own potential energy function. So then this equals then, and I'm going to call this F, or work non-conservative net. But then all the conservative forces have their own potential energy function, plus then there's the non-conservative net that is acting on the object. So in that case, you get that the change in kinetic plus all the potentials is not equal to 0, but is equal to the non-conservative net work that is being done on you. So again, I can have a ball moving down a ramp, which gravity is a conservative force, but maybe the ramp is sandpaper, so there's friction. Friction is going to be doing negative work, so I'm going to end up at the bottom of the ramp where gravity is going to be doing positive work all the while, trying to speed the ball up. And maybe it does still speed up, but not as much compared to if there was no friction, because there's negative work that's being done by the friction as it skids down the ramp. And and you can still calculate how much work that is, or maybe you can evaluate if you knew it starts from rest, if it starts from rest and it ends at the bottom of the ramp with some particular velocity, you can calculate how much work is being done by all the forces, or maybe you can evaluate the work that's being done by gravity and then figure out by this work energy theorem statement how much work was done by friction as a result. This all, though, amounts to us being able to have this function for the potential energy. So let's do the 1D examples are pretty easy. One of them will require us to go into spherical coordinates, and then the 2D multi-D examples are a little bit more involved, but still not too bad. So let's just go through them all briefly. Constant gravitational force. It's a constant function, so very easily I can write down that the curl is going to be 0. So that means I can define a potential energy function due to gravity as negative the integral from some reference point to some arbitrary point of what looks like to be the vector 0, negative mg dotted with dr. dr in Cartesian coordinates again is dx, dy, and dz if we were doing multi-dimensions. So then this looks like it's the integral from r naught to r of, after I take the dot product, of mg dy. So since this has turned into a simple 1D integral, truly really 1D because mg is a constant, so I don't need to know about what's going on in the x and the z or any other dimension. This really is just mg, the integral of dy. So in that case, rather than write this as vectors, I can say it's from some reference point y naught to some arbitrary point y, which then gives me the answer mg y minus y naught, where y naught is a location that I get to choose, which is going to correspond to where the potential energy equals 0. So most generally, I can write that this looks like it's just a function of y. This is mg y minus y naught. If you're used to seeing something like mgy or mgh, again, they were making a choice, as they were in that case picking y naught to be 0. Whatever y equals 0 is for that coordinate system is where the potential energy equals 0. But again, it does not matter. Again, let's just take super trivial example. There's some height h, and I drop a ball of mass m from rest. It falls. What can I say about the velocity of the ball when it hits the ground? You could do this with kinematics. You could solve Newton's laws of motion, of course, and that would give you the answer. You could also do this using an energy argument. If you're dropping this from rest, then during the fall, only gravity is acting on the object. We just convince ourselves that gravity is a conservative force. I expect conservation of energy to be obeyed, which means that delta kinetic energy plus, in this case, u gravity better equal 0. Or T plus u gravity at the start better equal T plus u gravity at the end. Let me just pause to appreciate how powerful that statement is. Because when we did this for particularly, for things like with momentum and angular momentum, but often in those cases we had to worry about, say, collisions going on, right? So we were worried about just at some point t, and then at some point immediately after at t plus delta t. Here, it can be, the start could be, the ball could be falling for minutes, and it does not matter in this case. It's only what's happening, so we can connect two spots presumably very disconnected in time, and you still know that the total energy must be conserved. So let's do that here. So in order to know what u sub g is going to be, we need to make a choice about the reference point. So let me first assume that the reference point is at y equals 0. Again, notice that is where I'm saying if I plug in y equals 0, the entire potential energy function is 0. So then it starts from rest, so the initial kinetic energy is 0 plus, and it starts a height h off the ground, and then it ends with some kinetic energy, and then it's located at y equals 0, so it has 0 potential energy. So in this case, it looks like V is the square root of 2gh in that case. And again, just to make it crystal clear that this is not new magic, again, if you want to ask, what is the work that gravity's done, which is the gravitational force over the path you took, going from y equals h to y equals 0? Well, this path integral, which we're taking as to be in a straight line, looks like it's just negative mg dy from h to 0, which again, that looks like this is then just mgh. So, yes. So in this case, gravity did positive work. Not too surprising. The ball speeds up as it falls. So by associating that possibility to do that positive work as it having a positive kinetic energy at the start, you can think of the potential, sorry, I said that wrong. If we wanted to associate, the potential for the gravity to do positive work as it falls, we can associate that positive work with a positive potential energy that it had at the start. That was energy that was kind of banked, that then gravity could cash out and turn into work that it does on the object. So I don't know how your intro physics professor did it, but I always use the analogy of think of energy like a bank, or just a monetary system. Your money is kinetic energy, which has one particular form, dollar bills. But you can take that money and put it in a bank, where then it has potential to be used at some later time. So that might be potential energy in that case. You can then, or it might be that you could take your money and buy an object, which then the object has a value equal to the amount of money you put into it. So you've transformed your money into something else, now this object, but it still has the same monetary value as you paid for it. And in theory, in kind of a completely equal economy, if you then sold that object, you would get the same amount of money back, and that would turn back into your kinetic energy, your money. That might be an example of a conservative force interaction, versus if I take my money and I buy a plane trip to go on a vacation, I get something out of it, but I can't get the money back after that experience. That is money that's been lost. It's kinetic energy that's been lost. It might be a non-conservative force acting on me. Or I might get, an investment from, say, a relative sends me a birthday card and there's money in it, That's an investment. That's not money I could then, I can then use to do new things. I've increased the amount of energy in that case. Another non-conservative example. But what if I said, okay, but I want to instead say that the potential energy is 0 at the top. So I say that my potential energy function is y minus h in this case. Well, conservation of energy still applies. No kinetic energy, plus at the top, my kinetic energy is mg, I guess 0 in this case, sorry. So my potential energy at the top is 0, because y equals h. Then at the bottom, I have kinetic energy. But then I've gone from y equals h to y equals 0. So then if I plug in y equals 0, it looks like then I have negative g mgh at the bottom. Then that just is the same answer, You're going to get 2gh in the square root as your velocity. So same thing. Because again, it's the change in potential energy that has meaning. So whatever that arbitrary constant is, ultimately will not matter. I was thinking of saving springs until we got to oscillations, but we might as well do it now. Let's take the 1D spring. Something that exerts a force parallel to the spring in a manner that, if it obeys Hooke's law, it's a force that is linearly based on its displacement, how stretched it is or how squished it is. I can't really do squish for kind of this elastic string, but in this case where I'm just perfectly holding it straight, there's no tension really, there's no restoring force. But if I pull it down, there is now a force on the apple that wants to move it back up. It's not a very strong spring, but it wants to then move it back up if I let go. If I double the amount of stretch, if this is an ideal spring, if I double the amount of stretch, the force doubles as well. How it translates into a force is usually given by a constant called the spring constant, if it obeys Hooke's law. Usually you probably saw this as negative kx or something like that. We can be a little bit more sophisticated now because, again, if this is a spring, there is a location, if my hand is the wall, there is a location where it's neither stretched nor compressed. So it's kind of at the location where the apple is now, where that is the position where there's no force. And if I move it beyond that location, should be a force back towards my hand. And if this were a spring, if I squished it in, there should be a force that's pushing it back out the other way. So for a 1D horizontal, and let's just keep it horizontal, right? I might say it's negative k because it's the negative because it's restoring. I want it to be in the opposite direction as kind of, if it's stretched, I want it to move back. If it's squished, I want it to push out. But instead of just writing x, I'll write x minus some equilibrium x. So this kind of location where it's neither compressed or stretched. If you wrote it as just negative kx, really what that was saying is when x equals 0, that's where it's neither stretched nor compressed. Which again, maybe you then just define your coordinate system such that that's the case. But in the case of the wall, usually you call this the origin, and there might be some location here where it's neither stretched nor compressed, and then the box is located here. So in that case, I would expect the force to be pointing to the left. And if you look at the force vector, that would be the case. If x is greater than x equilibrium, the entire thing in the parentheses is positive, so this entire thing is negative, so it's pointing to the left. If x is smaller than x equilibrium, this entire thing is negative, so this entire thing is positive, so it's pushing out to the right as a result. So, is this conservative? Well, this depends on position, so it might be a little bit more complicated, but it's not too hard to convince yourself that, right, partial with respect to x, partial with respect to y, partial with respect to z, then it's negative k x minus x equilibrium 0, 0. It's pretty easy to convince yourself that this will also equal 0 as a result. It only really is a function of x, but notice that all the partials that touch that term will either be partials with respect to y or partials with respect to z. So it's never possible to have this not be anything but 0. So this is these restoring forces where this negative sign is kind of pulling you back towards equilibrium. Right? Pushes back to equilibrium. If that negative sign wasn't there, that means if you were a little bit off from equilibrium, you'd want to then drift even farther away. That'd be an unstable situation. This then suggests there's a potential energy function. Then I can write U spring is going to be negative the force from a spring dotted with dr from some reference point to some arbitrary location. When I do that dot product, it looks like I get integral of k x minus x equilibrium dx from some, or ultimately ending at some arbitrary x. And now I have to make a choice as to what I think my 0 point is going to be. And again, you are free to make it be whatever you want. But one that might make sense is let's let that equilibrium point be where there's no potential energy in this case. And this isn't too bad. It's not bad. Easy. It's an easy integral to do by itself, but I might do a u substitution anyway. Do u as that thing in parentheses, then du as dx. At the end of the day, this then becomes 1/2 k u minus, or x minus x equilibrium all squared as a result. And again, that is for a particular choice of reference point where when x equals x equilibrium, the potential energy is 0. And again, as a sanity check, if I take the gradient of this function, well, in the x component, that's going to be, I'm going to take the x derivative, so it's going to be 1/2 k, then the x derivative is going to pop down to 2, x minus x equilibrium, chain rule, that pops out of 1, so that doesn't matter. And there's nothing in the y. And then there's an overall negative sign out front. Then notice the 2's cancel, and it looks like I get negative k x minus x equilibrium, comma 0, which indeed was the original force for the spring. So always a good check for yourself. You should be able to take the negative of the gradient and get back the force you started with. If you do, you did the integral correctly. If not, something's awry. So then let's do a quick simple example. I have a box that's attached to a spring, and it's starting from rest at a distance of 2 x equilibrium away, kind of out to the right. And I might want to ask, what is the velocity of the box when it passes through the equilibrium position, say? So what is the velocity of the box when it gets to this point? Well, I should first make sure, do I expect this to be a conservation of energy problem? Yes. Right, there's the spring force acting on the box, that's a conservative force. Technically, there's also gravity acting on the box, which is conservative, but there's no vertical motion going on, so even though I could write down a conservative function for gravity, it's never going to change value, and only changes matter, right? Only have meaning. So I could ignore gravity, I guess. But then there's also the force from the ground pushing up on the box. And that force I don't expect to be a conservative force because it can adjust its value to be whatever it has to be. But it is always moving perpendicular to the direction of motion. So it does no work as a result. It does no work as the box moves back and forth. So while there is a non-conservative force, it's never doing any work, so I can still apply the conservation of energy. The initial kinetic plus potential better equal the final kinetic plus potential for the spring in this case. Starts from rest, but it is then extended out to xe. Then it ends with some final kinetic energy. And then it's also at the final spot, it's located at x equals e, where there is no potential energy as a result. There's a 1/2 on everywhere, so I'll cancel that. So it looks like it's k x sub e squared equals mv squared. So then it looks like it's k over m x sub e squared equals v squared, or that v equals plus or minus square root of k over m times x sub e. Really absolute value of x sub e, but it's fine because we've defined to be a positive number. So again, it's not telling you whether it's moving left or right, but it is telling you the velocity. And we have some intuition that we know that we should take the negative sign in this case. Really, we should do negative that as the answer. But again, energy doesn't tell us that because it's always dealing with scalars. It can never tell us the vector direction when we're dealing with potentials. All right, that's another one. There is, let's see, which one do I want to do first? Let me do a kind of general function. Let me do it via example. What if I tell you the force is x squared comma negative y comma 1 in 3D? Is this a conservative force? Well, I'll let you test it out, and you can show that this indeed has a curl equal to 0. So this particular force field is a conservative force field, whatever it is. So I know a u exists in this case. So I can write down that u for this particular function is negative the integral of the reference point to some arbitrary point f dot dr. Now for the reference point, let's just make our lives easy. Let's use 0, 0, 0 as our reference point. Again, you could make it be whatever you want. I'm going to make my life a little simpler. R then is just the general x, y, z. And so this looks like that then the potential energy function is negative going out from 0 to x, y, z of this function dotted with dr. And since the potential energy should be independent of the path you take, technically you can choose any path that goes from 0, 0, 0 out to this arbitrary point, and that should allow you to write down the potential energy function. However, when you're trying to devise what this potential energy function is from scratch, that can be very complicated because if you take any arbitrary path, then as you're moving along that path, x, y, and z could all be changing simultaneously, and you would need to keep that into account as you evaluated this line integral, which might then make this entire integral pretty complicated. So while this is true for any path that goes from 0, 0, 0 to x, y, z, if it's true for any path, then it's true for a very specific path that will always guarantee you to get the right answer. So kind of the path to use is one where you restrict yourself so that every variable is only changing one at a time, rather than x, y, and z all changing simultaneously as you take some weird path to the point. Have it so you go first along the x direction, then along the y direction, then along the z direction to get to your point. So you would use a path that, say, goes from 0, 0, 0, and then maybe it goes out to x, 0, 0. That's one part of the integral. Then the next path goes to x, y, 0. Then the final path goes to x, y, z. If you evaluate that line integral, you go from your reference point ultimately to your arbitrary point x, y, z. But notice in each case, you're only letting one variable change at a time. Particularly for this line integral, dx is the only thing that really matters. dy is 0, dz is 0. So I could say dr in this case is just dx, 0, 0. And then also notice that y itself and z itself are 0 in this case, because they start at 0 and they stay 0. In this case, it's only really dy that matters. And then x is just a constant, right? You just hold it as x, but then z is still 0 while y changes. And finally, your dr is 0, 0, dz. and x and y are constants, and then z is allowed to change. So let's see how this looks in practice. So essentially you have three integrals you need to do. Integral 1, integral 2, integral 3. Whatever those three answers are, you add them together. That's your potential energy function. So for integral 1, your force then simplifies to, we've lost it, there it is. So again, for integral 1, we're only moving along the x direction, but while y and z are still 0. Maybe I'll draw it real quick just so you can visualize this. If this is the x direction, the y direction, the z direction, and you're going out to some arbitrary point, which is located at some x, y, and z value, or whatever those values are. The path integral we're going to take is start at the origin, go out to this point, then go out to this point, and then go up here to get to your... So ultimately, that takes you from the origin to your arbitrary point. And since any path is good, this works. So during path 1, since x is allowed to change, we'll keep x around. So this is still just x squared, but y is 0 and z is 0. So then along that particular path, that's the force vector. dr in this case is then dx, 0, 0. F dot dr then looks like it just becomes an integral of x squared dx. And again, you're going from 0 out to some arbitrary x along that path. So then that looks like it's x cubed over 3. And I'm going to throw an overall minus sign in at the end of the day. 2. Now x is a constant. But then we have y, which is allowed to change. And, oh wait, what function did I give? Oh, sorry, I did not give z. This should technically have been 1. Doesn't change our answer because the dot product still would have gotten rid of it. While z equals 0, z doesn't appear anywhere, technically. So x squared is a constant, and then you have negative y, which is what's changing, and then the z component is 1. But that's fine, because dr is going to be 0, dy 0. So the integral of f dot dr is the integral of negative y dy as you go from 0 to y. So it looks like it's negative y squared. As a result, over 2. Then the third integral, the force vector is x squared, which is a constant, negative y, which is a constant, comma 1. dr is 0, 0, dz. F dot dr ends up being from 0 to z of just dz. So it looks like the answer is just z at the end of the day. So then your potential energy function is overall negative sign out front, x cubed over 3 plus, minus y squared over 2 plus z. Or if you take in the negative sign, negative x cubed over 3 plus y squared over 2 minus 1 is your overall potential energy function. And again, you can confirm that negative the gradient of u gives you back the vector x squared comma negative y comma 1 when you take the gradient. So that would be the potential energy function. If I then gave you start at the origin and you go out to 1, 1, 1, you could easily evaluate the work that's being done there. Right? The work of this force going from 0, 0, 0 to 1, 1, 1, Well, you could, again, do this line integral brute force way, or you could realize that since this force is the negative of a potential energy function, 0, 0, 0, 1, 1, 1, this then is going to be negative u evaluated at 1, 1, 1, minus u evaluated at 0, 0, 0. So then it looks like it's negative. Let's see, I plug in ones for everything, so it looks like it's negative a third plus 1/2 minus 1. Then I subtract from that when I plug in 0 to everything. Looks like I just get a negative 1. The negative ones cancel. This looks like then it's 1/3 minus 1/2, or negative 1/6. That would then be the amount of work that is done in going from the origin to 1, 1, 1, done by this conservative force function. And again, you might, as a way of practicing your line integrals, actually do the line integral manually and see that you get the same thing. All right, let's see how we're doing time. I think I'm going to hold off on the spherical integral 1 and do that in the next module. I think it will fit in the next module. So then the last thing I want to do for today is talk a little bit about graphical representations of potential energies. Particularly, we're going to focus on the 1D case, because those are easy to graph. In 1D, the gradient then, it's not a vector, there's only really one term. So for simplicity, let's use the x direction as the single term. Really then this becomes just the derivative of du dx in 1D. So in that case, the 1D force is then negative du dx in 1D. And we don't have to worry about gradients or anything like that, since we don't have to deal with vectors in this case. So the force, again, now thinking back to just simple derivatives, the force is the negative value of the slope of the potential energy function. So if I have a potential energy drawing where as a function of x, I am plotting potential energy, and perhaps it looks something like this. I could ask myself what's going on at various locations. If I'm located here at some x value, the potential energy has a certain value, a specific value. And while I was saying that the actual value of the potential energy doesn't have any physical meaning, because it has this arbitrary constant you can throw in, that arbitrary constant goes away when you consider derivatives. So thinking of the slope of a potential energy function at a certain value, that actually still has some interesting information, because that is saying something about the force. In this case, if the force is negative the slope of the potential energy function, at that point in red, the slope is negative because the thing is going down. The negative of a negative is positive. That then says that the force is pointing to the right. At this location here, the slope is positive. Throw in an overall negative sign, the force then is pointing to the left. Which is kind of nice for 1D potential energy functions, because then you can kind of think of it kind of like a roller coaster, right? If you're at this location, you expect to kind of be as a result to move to the right. and that is what is kind of matched by this potential energy result. When you're over here, you expect to kind of feel yourself falling to the left, and that is what is matched by this potential energy function. What then is also interesting is what is going on at this bottom spot. Well, there the slope is 0. So then the force is 0 in that case. What is going on at this point? Well, the slope is 0. So the force is 0 at this case. And if you had multiple one-dimensional forces, then you could make a plot like this that is kind of the sum of all the potential energies. And there might be a location, right? So this might, maybe I'll just upgrade this. Like imagine this is the sum of potential energies that is acting on the object, and it traces out this interesting curve. By looking at this curve, it seems like there's something going on, because then if there's multiple functions, that means there's multiple forces. So then I could write F nets underneath all of these. So since often we are interested in things like equilibrium, the equilibrium points where F net equals 0, we can actually still figure that out from energy alone. We don't have to do force diagrams. If I know what the potential energies are, it looks like that these equilibrium points where F net equals 0 are where the derivative vanishes. So where the first derivative vanishes. So, so force balance locations are where the first derivative is 0 for the sum of all your potential energies. But not all equilibrium points are created equal. If I'm a ball in the bottom of a bowl, that is what I might consider a stable equilibrium point, because if I nudge the ball in any sort of direction, it will wobble around, but it will stay relatively in the same spot. It will stay near the equilibrium point. Whereas if I have a ball at the top of a hill, well, I nudge the ball even a little bit in any one direction, and then it rolls away, farther and farther away from the point of equilibrium. That first case is a region of stability. A stable equilibrium point, where at the top of the hill, that would be an unstable equilibrium point. Right? There's one infinitesimal spot where the forces all vanish, but if you nudge it a nanometer away from that spot, it will slowly but surely roll away. Well, that's exactly what this kind of valley and peak that I drew on the potential energy diagrams are corresponding to. This is a region of stability, or an equilibrium point of stability, and this is an unstable equilibrium point. Again, put it at the top of the hill at that exact spot, and if it's not moving, it won't move beyond that. Nudge it a little bit, it will roll away. Put it at the bottom of that valley, nudge it a little bit, it will probably end up oscillating. We'll actually get to that. It will actually undergo simple harmonic motion around that point. So then, is there a criterion for stable equilibrium points? So the valleys are where, well, it's an equilibrium point, so I still require the first derivative vanish. And what's the difference with the valley versus the top? Well, it's the concavity, right? If it's concave up, that's a valley. If it's concave down, that's a peak. For a 1D function, concavity, remember, is saying something about the second derivative. So this is also where the second derivative is positive. It gives you a stable equilibrium point, because that says that you're caving up as you go away from the equilibrium point if you're concave up on both directions. Versus if the equilibrium point had a negative concavity, right? That's like a top of a hill. So that can be viewed as kind of stable equilibrium points and just kind of locations of equilibrium points in general. And this upgrades, of course, to multidimensional potential energies as well. For 2D, right, if you have a function that's a function of x and y, you can recall from Calc 3 that it's where the gradient of that function vanishes where you have a max, min, or saddle point. So right, you're finding where the gradient vanishes for a 2D function. And then you had that funky determinant thing where you had the second derivative of the function multiplied by, with respect to x, multiplied by the second derivative of the function with respect to y, minus the square of the mixed partial derivative. If that is positive, negative, or 0, it tells you if it's concave up, down, or whatnot. And that function that I just referenced, right, is actually an example of a more general thing you can do called a Hessian matrix, Hessian, that can tell you for a 10-dimensional function whether it's concave up, down, or whatnot. But let's just stick with 1D. So let's see, for example, if I had a function where this is my potential energy, let's just stick with one potential energy, and maybe this is u sub 1, this is u sub 1 divided by 2, and then this is 0. If you release a particle from rest at x naught, and x naught, let's have it be right here. You can say things like, is the particle bound? Where can the particle roam? Is it possible it can travel away to x equals infinity, or is it stuck, in some sort of location? And let's let this be the only force acting on you. Well, in this case, energy is conserved. So whatever the energy is at the initial spot better be than the energy at any subsequent spot, or what we were calling the final spot, earlier. So if it's released from rest, there's no kinetic energy, and it looks like it has a potential energy of about x naught over, or y naught over, u naught over 2 is the total energy of the system in this case. So no matter what the particle does, its kinetic plus potential better always add up to u naught plus 2. We could make that a red dashed line as it goes out. So if that red dashed line is the total energy, the particle can never exist above that line. Because if it exists above that line, its potential energy would be greater than u naught plus 2. And kinetic energy is always positive, so you can't add a kinetic energy to bring it back down. So this then, for this particular example, where energy is u naught plus 2, this region then becomes forbidden. Because to live in that region means that your total energy exceeds what must be your total energy based on energy conservation. So if you started here from rest, that essentially says you're limited to just kind of roaming around in this valley, right? You could roam back and forth, over and over again, and you would kind of come up to this point, and then you would find that once you get to the spot on the other side, right, at that spot, u equals u naught over 2, and so then your kinetic energy better also equal 0 there, because it still needs to add up to u naught plus 2. At one of these locations deeper down, right, u is then going to be less than u naught over 2, which then allows your kinetic energy to be something positive, because then it can be whatever it needs to be to add up to u naught plus 2. So then kinetic and potential are just exchanged back and forth over and over again. But in that case, that's an example of a bound system. You can do this in electromagnetism and quantum mechanics. When are electrons bound to a nucleus? if you can figure out the potential energy function, you can find that there's a region very close to the nucleus where the electrons become bound to the, to the atom or molecule or whatever. But if it has enough energy, it kind of looks like this if I were to draw it. And I'm blanking on the names of the scientists, where essentially it looks something like, right, kind of drops down and then kind of, comes up and then plateaus because of the Coulomb 1/r², dependence. So if you had an electron whose total energy was something like this, then that means the electron would be stuck somewhere in this location near the nucleus. But if the electron had a total energy that was this, maybe it had a lot of kinetic energy, for example, then that means if the electron is starting here, there's no reason why it can't then just roam and travel away forever. Because it always will have it can have kinetic energy to keep it moving out there without it all becoming potential energy. Because again, it's just really an exchange. All right, and I will save the spherical coordinates one for the next module.